For this review problem, we have the motion of a spring, u double prime plus gamma times u prime plus 81 times u is equal to 0. And we're going to determine if the system is overdamped, underdamped, or critically damped for these three different values of gamma. All right, let's start with 8. So u double prime plus 8u prime plus 81u equals 0. So we'll start with that. Okay, so we get the characteristic equation, r squared plus 8r plus 81 is equal to 0. And we'll use the quadratic formula to solve for r. So we have negative 8 plus or minus square root of 64 minus 4 times 81 divided by 2. So negative 8 plus or minus the square root of 64 minus 324 works out to be negative 260 divided by 2. And so this is equal to negative 4 plus or minus. If I divide this by 4, I get 65. So I times square root of 65. And that's about as good as it gets. And so our solution is going to be u of t. I'm going to bring it down a line. U of t is equal to c1 e to the minus 4t times the cosine of t times the square root of 65 plus c2 e to the minus 4t times the sine of t times the square root of 65. And so that is going to be our general solution. We have a complex roots, so this one is underdamped. Now, if it's underdamped, there is a quasi-period. So the length of the quasi-period is going to be 2 pi over the number that's multiplying the t there, so 2 pi over the square root of 65. And so that's the length of the quasi-period, whatever that is. Now, what does a quasi-period mean? That means that if I take u of t plus 2 pi over square root of 65, that's going to be equal to c1 e to the minus 4 t plus 2 pi over square root of 65 times the cosine of t plus 2 pi over square root of 65 times square root of 65 plus c2 e to the minus 4 t plus 2 pi over square root of 65 times the sine of t plus 2 pi over square root of 65 times the square root of 65. So that's equal to c1. Now I'm going to break up these exponentials from negative 4t e to the minus 8 pi over the square root of 65 times the cosine of, if I multiply this out, I get t square root of 65 plus 2 pi. Then same thing on the second part. I get plus c2 e to the minus 4t e to the minus 8 pi over square root of 65 times the sine of, multiplying out, t square root of 65 plus 2 pi. Okay, now there's an e to the minus 8 pi over the square root of 65 that's common to both. I get c1 e to the minus 4t. Then I have cosine of t square root of 65 plus c2 e to the minus 4t times sine of t times the square root of 65. And this thing in parentheses, of course, is the function u that I had in the first place. So if I go forward in time by this much, my period is displacement is going to be the same as what I had before, but multiplied by this damping factor. So this damping proportion is going to be equal to e to the negative 8 pi divided by the square root of 65. And that tells me roughly how much the motion has changed from one period to the next. So real quickly on my calculator here. I'm going to try to get this and hopefully not make a mistake when punching in. Negative 8 e to the negative 8 pi. So let me show what I'm doing here. So e to the minus 8 times to the pi. Where'd it go? Divided by the square root of 65. And so this works out to be about 0.0443. So it loses, so the amplitude is only 4.4% of as much as it used to be after one quasi-period. Okay, so that's one problem. Now let's go to the next part of the problem, when gamma is equal to 18. So starting over, we get that u double prime plus 18u prime plus 81 is equal to 0. Characteristic equation is going to be 18r squared plus 18r plus 81 is equal to 0. And this factors r plus 9 squared equals 0. And so this gives me my solution. U of t is going to be equal to c1 e to the minus 9t plus c2t e to the minus 19. So this one is critically damped. Okay, last part of the problem is when gamma is equal to 28. So we have u double prime plus 28u prime plus 81 is equal to 0. That gives me my characteristic equation of r squared plus 28r plus 81 equals 0. So let's use the quadratic formula to solve for r. Negative 28 plus or minus the square root of 28 squared is 784. Minus 4 times 1 times 81 is 324 over 2 times 1. So that's equal to negative 28 plus or minus the square root of 460 divided by 2. So that's negative 14 plus or minus square root of 115. And so the equation of motion will be u of t is equal to e to the negative 14 plus the square root of 115 times t, c1, plus c2 e to the negative 14 minus the square root of 115 times t. So this one is overdamped. I have two distinct real solutions, so this system is overdamped. Now, for the last part of the question, for which system does the motion decay the fastest for these three cases? The answer is going to be for the critically damped case. Negative 9 is going to be the highest, or negative 9 is going to be the smallest, the most negative exponent that I see in these three answers. So that was negative 9. My first answer was, I had a negative 4 here, so that doesn't decay as fast. The critically damped case is negative 9. The one I just did, I've got these nasty square roots. The bigger one is going to be this one, so I'm not going to even worry about computing this. So if I compute this on a calculator, I get negative 14 plus the square root of 115, which works out to be negative 3.276. Once again, that's not as negative as negative 9. So the one that decays the fastest is going to be the critically damped case.